Happy New Year. It is time for another Let's Make It, the first one of 2014. And Bob is back. And tonight he's going to show us how we can time things with the 555 timer. Coming up right after this. Hello and welcome to Let's Make It. It's been last year since we did a video. It's been 3 weeks since we did our last video, and we took the end of December off. So we just took a little bit of time off, do some read stuff in the studio here, some projects that were going on, things like that. And this time, I also am lucky enough to have Bob back with me. How you doing, Bob?
I'm doing great.
So,
it's good to be back.
Yeah, good to be back.
Yes.
Yeah, you had a little bit of a rough time there, didn't you?
Yeah, spent most of the month of December in the hospital, so it's nice to be out and back with the living again.
Yes. All right, so this week, this is episode, I didn't say this in the beginning, this is episode number 48, and recording on the 6th of January, 2014. I almost did 2013, I'm still doing that. I keep correcting myself.
Well, it'll take a little while, yeah.
Yeah. And I do want to thank anybody who used our link to buy things through Amazon in December. You don't have to stop. You can use that all the time. It's still there, so you don't have to stop using it just because the Christmas is over. I also want to thank people that have been telling their friends about it. This show's been growing really fast. Even in December when we weren't doing shows, our download number still stayed very high on the old shows. Just so everybody's, spreading it around or finding it on the internet or whatever, telling your friends. Definitely appreciate anything you're doing to help us spread that out. I was a little concerned about tonight, and looking at the chat room, I was probably right. Taking some time off like that generally gets people out of the habit of coming to watch live, and I don't think we have anybody in the chat room today other than Bob and I. We did somebody in there. Jim from Canada was on there a little bit earlier, but he's not on there now. But we're back to normal, so we're recording every Monday. The vacation's over, or what was supposed to be a vacation, I guess, is over.
Yeah, it's time to get back to work. It's January now.
Yeah, actually, I worked pretty hard during that time off with things around here, so that's a fair warning. Things are going to break possibly during the show because lots of new things that we're using. In fact, something already broke. If you're watching this, you don't know it because we had to restart our recording because of it. So before I let Bob get into his discussion tonight, I want to talk about some things that I've actually gotten in the last few weeks that I really haven't had time to play with yet, and I'm really itching to play with it. This first one is a beagle bone, and it is it's similar to an Arduino, but I think it's considerably more complicated. It can do a lot more than an Arduino can do. The little bit that I've read about it, there's a lot more it can do, but it takes a lot more work to make it do things. Arduino is designed to be a real quick prototype and learning tool, where this is originally designed to be a teaching tool, but it's definitely much more complicated. But I'm looking forward to it because the switcher that I have developed, I am running out of memory. In fact, I want to do a show in a couple weeks about memory management because I've learned a lot the last couple weeks in memory management. And then the other thing here, and I actually got two of these, it's called a Spark Core. And it comes in, it was a quick Kickstarter project. And let me pull it back out here. It's on a breadboard right now, but basically it's a dip device. And if you take it off and look at it, the top side of it is a Wi-Fi interface, and the bottom side is a micro, I think it's what's the real small Arduinos? Micros, right? Or minis?
The mini.
Mini. Okay, so I think it's a mini that's in there. So it's all in one chip, and it's a Wi-Fi. And I want to do a whole show on Wi-Fi, and I've been meaning to do it. This may just get me to do it. And I have a project I want to do also that requires Wi-Fi. So this may be the catalyst that gets me going on that as well. And this last thing, Bob's going to know, it is a 16 by 16 LED array that I got off Kickstarter, and.
Sweet.
Yeah, they are. I
want one.
I can't wait to get the power supply. I actually don't have a power supply big enough to run it. It requires a 15 amp 5 volt power supply, and I don't have one that big. I've never I don't think I've ever owned one that big, actually. So when you order them, they're actually quite large, and they do make them. They're just for LEDs, for the LED panels and the LED strips. This uses the individually addressed chips, which is the WS 2812s. So each of these chips has a little mini shift register in it. So you basically program them like you do a shift register, or very similar. And there's plenty of code out there on the internet that can do that. And then today, Bob is going to talk about some timers. We're going to learn how to time things using a very popular utility chip, the 555 timer.
Yeah, this is pretty much a back to basic electronics kind of demo where we're going to show how, a couple uses of the 555 timer chip. And the problem with coming up with demos for this chip is it is so flexible, and there's so many different ways you can use it, and so many what you can dream up is the limit of what you can do with the chip. So I've put together a couple little demos, and we'll walk through it and explain how things work. And it's very flexible, and hopefully we can spark a few ideas with it.
All right.
This is definitely a basic IC that. Oops. Sorry about that.
That's okay.
Back to a basic IC that everybody should, if you're going to do electronics, this is a chip that you've got to have in your pocket somewhere to pull out sometime, because it is so flexible and useful for all kinds of projects.
Yeah, it definitely is one of those utility things that you see everywhere. You see lots and lots of them.
Oh, yeah. And I think it was the Wikipedia page that I read that somewhere about 10 years ago, more than 1 billion of these things had been sold worldwide.
That's a lot.
In their various forms. So that's a ton of chips.
Yes. All right.
So we ready?
Yeah, let's go.
All right. Well, 555 timer chip. The ones that I've got tonight are basic TI general purpose chips. You can get them just about anywhere for less than $1. Let me switch to the desktop, and we can look at a diagram of it. So here's a 555 chip. And when you use it, basically you have 3 different modes that you can run this in. 2 of them I've got a demo on. The third one, I've never actually seen it used in the real world. But the first one is a monostable configuration, which is actually this diagram right here, which essentially means that you hit a trigger and you're going to have the output go high for some period of time, and then it shuts off. And it's kind of a one-shot deal. You hit and in my demo, I've just got a push-button switch, and that's it. And then you've also got what's called astable, which is this diagram right here, which generates some sort of pulse. And this could be anything from, you could use it to generate a PWM signal. You could use it to generate a pulse for a tone generation. Anything that requires, a square wave signal right there, you can use. You can use this configuration. The third one is called a bistable, which essentially turns the 555 into a flip-flop. And in my experience, it's just easier to use a flip-flop than to try to get a 555 timer chip to function that way.
Yeah, because they're purpose-built to do that. They're a little bit easier to...
Right.
Less parts even.
So, yeah, less parts, easier configuration, although you can do it if you want. But I've never actually seen it used in the real world that way. So here's a typical chip, what it looks like in a dip package. And of course, ground is ground. And we'll just go through the pins, um, you know, in numerical order. The ground, that's obvious. The trigger is what starts the timing interval. And we'll talk about the timing interval here in just a moment. The output, when the timing interval starts, output goes high. And high is essentially, depending on which chip you get and which variation you get, it's usually about 1.7, 1.8 volts below whatever your supply voltage is. So in my demo, my supply voltage is 5. So my output, I'm running 3.3 volts. The other one thing about this is the output also, if it's not high, it's tied to ground. So you can actually have something where current is flowing back through this, going to ground, and that's in one of my demos. I'll show how that works. The reset chip, pin 4, is exactly what it is. This one, in most chips, if you send it to ground, it will completely reset everything in the chip. Although different manufacturers, somebody will have to read the data sheet to find out exactly how the behavior is. Different manufacturers do things a little differently. Some of them will halt the timer right where it's at and leave. If the output is high, it'll leave it high. If it's low, it'll leave it low. In general purpose, it usually just shuts off the trigger and the output goes back to low. The pin 5, the control, and this will actually make more sense here in just a minute when we talk about the threshold pin, number 6. But the control pin allows you to change the default behavior on the pin or on the chip, which gets us to pin 6. And this is actually the core of the chip. Is the threshold you use. 555 timer chips are always used with capacitors and resistors. And essentially what this timer chip is, it's really not a timer, it's a comparator. And what it's doing is it's comparing the source voltage, whatever that happens to be, to the threshold voltage. And by default, it is roughly 2/3 of that voltage. And there's a reason for 2/3 that we can talk about if we have time in the show. But essentially, it's 2/3 of the supply voltage. So if someone hits the trigger, output goes high, the threshold starts comparing, and when it gets to 2/3, then it shuts everything back off. The pin 7 is the discharge, and that's where the capacitor will actually dissipate whatever charge has been accumulated. So you're applying a charge to the capacitor. When it reaches 2/3, it shuts everything off, and then the capacitor immediately dissipates. And then, of course, pin 8 is the supply voltage. So does that make sense?
Sure does.
So far, so good, huh?
Yep.
I haven't. Okay. All right. So the first one that I've got here, oops, sorry about that, is actually in. I'm sorry. The first one I have is the monostable configuration. Now, one thing in this diagram, this is kind of a pin 5. In this diagram, they actually show a small capacitor connected right here. I don't have one. sometimes I've had a capacitor in there. Sometimes I just leave the pin floating. In this example tonight, I do have it floating. So, sorry about that. All right, let me switch to the camera. So here is a simple 555 timer, and well, I'll just here. So you press the button, the LED comes on, and what's happening is that big capacitor is charging, and this is a basic monostable configuration. So let me go through all the parts on this. We've got this is a 470 microfarad capacitor, so it's a fairly big capacitor. And then I've got 3 resistors here that I can show the difference in how quickly this capacitor can be charged. And then these resistors are just for the LEDs to turn down the intensity so they don't, so they're not so bright on the camera, because that seems to be a problem for me, is
Yes.
blowing out the camera. And then just a simple push button switch with a 10K pull-up resistor on it. So in this particular case, I've got this connected to the 10K resistor. So press the button, LED comes on. This capacitor is charging through that 10K resistor, and it lasts roughly 6 seconds. And with just a simple change in the resistor, so let me switch to the 2.1. Changing to that's a 2.2K resistor, and now instead of taking 6 seconds, it's just a single second. And then of course, if I come over here and go to this 47K, and we probably won't let this run the whole time, but this will actually run for 25 seconds. So this is you have something where you want somebody to press a button or flip a switch, and you need something to last for a certain period of time. Well, 555, this is how you do it. And the choices of how you get it done are really infinite, because you can change the capacitor and change the resistor, and you can get the same behavior from a multitude of different configurations. So now the other thing that we talked about a little while ago is the output is both a source of voltage, but it's also syncing to ground. So let me that off and there, and if it works right, that green LED it's actually being grounded through the chip.
So it's draining through the chip.
It's draining through the chip, and as soon as let me switch back to 5 seconds. As soon as I hit the button, the other LED comes on, and the capacitor charges, and when it gets to 2/3, then its time has run out, and it switches back, and it's back to being a ground. And of course, somebody might say, well, how can you have both LEDs connected to the same pin? Well, it is an LED. Current only flows one way. So if it's connected to ground, current's only going to flow that way. If it's the source voltage, current's running the other way, and LEDs are only going to allow current in one direction.
Right.
So its flexibility is tremendous. So, but you can have things run very quickly or very slow. it's all up to what you need and what components you have to put together the project. So,
all right. And this is the monostable one, right?
this is the monostable, and you can use pretty much anything you want as the trigger. Now, if you wanted to, you can use that control pin to change the behavior of the timer. Okay, so if you leave the control floating or connect it to ground with a capacitor like what was shown in that other diagram, then it's just going to be 2/3 of whatever the supply voltage is. But you can use that control pin if you want to change that behavior for some reason. In the real world, I've never bothered to do that because whatever behavior I'm interested in, I can find a capacitor resistor combination that gets me
to 2/3. Yeah.
Right. But it's there if you need it. All right, so that's the monostable. Now let me switch breadboards.
Well, I can take a break while you do that if you want.
Yeah. Take a break, and
all right.
I'll switch breadboards.
Okay.
You work hard for your business. Your website should too. No matter what industry you're in, select your customizable high-quality design with professionally written content and graphic elements created for your business. Make changes online whenever you like. Switch your background color, page layout, and text anytime. Add your pictures and logo. Upgrade your website with useful one-in-one web apps. And integrate social media. Upload your photo albums and embed videos. With one click, optimize your website for viewing on mobile devices. Choose your free domain, or you can easily transfer an existing one. Thanks to One-in-One's SEO tools, customers can find you everywhere. One-in-One My Website, a professional website created by you.
When you open up an Audible audiobook, it opens up your imagination. Enjoy a steamy romance while ironing the sheets. Discover an historic battle while battling the bulge at the gym. Visit audible.com/freebooks now to try 2 books absolutely free. Get caught up in a whodunit during a do-it-yourself project. Listen anytime, anywhere with the Audible mobile app. When you're out for a walk, learn how to climb the corporate ladder. Or bring a little magic to your minivan with a fantasy novel. With over 100,000 titles, Audible is an amazing experience that you can now try absolutely free. And just like our books, there's no binding. Our great listen guarantee lets you exchange a title you don't like for another. No questions asked. Visit audible.com/freebooks to download 2 books of your choice right now.
The biggest thing is that, first thing is this is generating a square wave. So you can use this to create anything where you have to have some sort of pulse that runs over and over and over again, this is the way to do it. And the one of the main differences about this is that the trigger is tied to the threshold pin. So what that means is that as soon as a cycle is over, it immediately triggers the next cycle. So it's constantly charging and discharging the capacitor. And and in this example, I actually have what you're looking at is I've got two different capacitors in here just to show the difference in how things work. And I've also got two different resistors in here and there are, if you search the internet, there are a multitude of calculators for astable timer chips. So whatever duty cycle you want, whatever frequency you want, there's a calculator out there, and I started to put one together and realized that, so many people have already done this that there is no sense in recreating the wheel for the millionth time. So I'm not even bothering with coming up with a calculator. What you're actually looking at here is a 100 microfarad capacitor, and in the calculations, and let me switch back to my desktop real quick. You have what's called R1 and R2. And essentially what it means is that you're charging and discharge. You charge the capacitor through R1 and R2, and you discharge the capacitor through R2 only. So you can manipulate those two resistor values and get what you want. So in this case, R1 is actually a 470 ohm resistor, and R2 is a 4.6K, which gets me 1.5 hertz and a duty cycle of roughly 52%. So when you're dealing with resistors and capacitors, there's always variations, because you have 5% and 2% variability in the resistors. There's always a little variance in the components. So
do you want to sell that diagram up a little bit?
Oh, this diagram?
Yeah. I can't. We can't see the bottom of it.
Oh, I'm sorry.
There you go. There you go.
All right. So in the example that we go back to in just a second, R1 is 470, R2 is 4.6K with a 100 microfarad capacitor, and this capacitor is not there. And the output, I've got it tied. I'm using the output as both a source and ground. So, and I've got the two LEDs wired up to switch back and forth immediately.
So they're just in there. They're on the same pin, just backwards of each other, right?
That's right.
Like the other one you had.
Just like the other one.
Okay,
right.
So the trigger, is it a 2/3 also?
The trigger is just, if it goes high, the output cycle starts, and as soon as it goes high, then the timer starts. The output pin goes high, and the comparison comparison of the source voltage to whatever the voltage is in the capacitor starts. So in this case, you can see that we're switching back and forth very quickly. Well, it's because the capacitor is charging very quickly.
Right.
Does that make sense?
Yep.
Okay. So this is the beauty of this chip, is that you can generate something very quickly. So let me switch. Let's see. Let me change. Undo this, and now So now I've got a completely different behavior because I've switched R1 from the 470. This is the 470K resistor, and this is another 4.6K resistor. So I've got it running through here. So now I've got 1 hertz, roughly, and a 66% duty cycle. So completely different behavior, and all I changed was 1 resistor out of the whole circuit.
Right.
So completely different behavior. And just for fun, I've also got a this what we're running right here is the 100 microfarad. I've also got a 4.7. That's the smaller of these two switch capacitors. Now,
Charger's much faster, doesn't it?
Yeah, this is, but it's still, this is 22 hertz. It's not, but that's how fast the capacitor is charging and discharging. And then if I want to ramp up the speed even more, if I switch back to the smaller resistor, which means it's going to charge faster. So there it is.
Yeah, from my point of view, I can't see it blinking at all.
Okay, well, it's actually running about 32 hertz, and yeah, I can't see it. It's faster than what the camera can pick up. But you can do anything with this. You need a tone generated. Well, a small capacitor and the right resistors, and you've got a tone generator.
Right.
And you can have it on whatever frequency you need. You need a specific pulse width that's consistent. And, we've talked about, what a Arduino can do at length on several episodes before. Well, if an Arduino can't do it, set up a 555. So it's incredibly versatile. And there we are back to.
Yeah, so I can see the one that's farthest away from the camera is blinking. The other one I can't really tell it's blinking.
Okay, and this is back to 22 hertz with a 66% duty cycle. So, you could even have one of these. You want to. I'll turn that off and let me switch cameras. You have a wide range of choices, and that's the beauty of this chip, and the frustration for doing a demo is that there's so many things you can do with it that it's hard to come up with a demonstration that even comes close to showing the capabilities of what this thing can do.
Did you change your camera?
I just switched back to.
I don't see you yet, so. There you go.
Oops, wrong button. Sorry.
That's okay.
Yeah, and that's the beauty and the frustration with this chip. And of course, when I started putting together this demo back, the middle or first part of November before Thanksgiving, I think Mouser has 4 dozen different 555s.
Right, and we should also probably mention a 556 is basically a dual 555.
Right. 556 is 2 of them in the same dip package, and then of course there's the 558, which is 4 in the same dip package. And what they do is they share the reset voltage and grounds to keep the pin count down. But you're still left with the same, multiple timers in a single package.
Right.
And of course, there's high voltage, low voltage. There's military spec parts. Whatever use you have, there's a chip out. There's a variant out there. But just general purpose ones, these were cheap. They were less than $1.
Right. So Can you describe the 2/3 thing a little bit? The math behind that?
The math behind that, depending on which textbook you read or which source you read, it's basically a capacitor charges itself on an exponential curve or a logarithmic curve, depending on which book you read. What does that mean? Well, it means that it's a curved charge. So in effect, 1 unit of time, you will charge about 63% of a capacitor. 2 units of time, you will get 85%. And it takes about 5 units of time to get to 99.9% charged, which is typically considered, fully charged. But when you start getting into that second, third, fourth time unit, the variation from one charging cycle to the next charging cycle starts to change. So what they did was they said, okay, forget all of that, fully charged stuff. We don't need that. We just need to be consistent. So we're going to use that first time unit in a logarithmic charge, or a logarithmic curve. And when you get to one time cycle, boom, there's your trigger.
Okay.
So it's very consistent, very repeatable. And that's why 2/3 is a great number. It's actually 63%, but the rule of thumb is 2/3. So, and supply voltage, and that's something else, is the supply voltage actually doesn't make a lot of difference for most applications, because 2/3 of 5 volts is a value. 2/3 of 10 volts is a value. 2/3 of 7.1235 volts is still 2/3. It doesn't make any difference what the supply voltage is. So, which makes it nice to get consistent results in a wide range of applications. Now, one thing about this is, somebody might say, well, why can't I make one that repeats every millisecond and use it as a clock? Well, the problem with that is that there's too much variation in your components. Okay, we were talking about numbers where it was, I was 1 hertz, 1.5 hertz, 22 hertz. These were the demos that I was coming up with. Well, the small variations in the components, well, maybe that 22 hertz, well, maybe it was really 21.8. Okay.
Right.
There's no way for me
at that point, that 0.8 is enough to take a timer off. 0.8 milliseconds, it adds up in time.
Yeah, if you're counting milliseconds and trying to do real clock timing, that's enough to throw you off very quickly. But for pulse width generation, one time, turn something on, that small variation isn't going to make any difference at all, one way or the other. So, yeah, if somebody needs an external clock, they need an crystal oscillator instead. And that was actually something I was talking to somebody about in email this last week, is using a crystal oscillator with an Arduino. So
actually, I think I saw that email to get accurate timing.
Yes,
it's funny.
Accurate timing.
It's funny that over this past couple weeks, we've had a lot of questions about countdown timers.
Yes,
quite a few of them. So it must be a popular subject. So at some point, we want to go back and relook at that again. I actually have that timer chip from NXP that I have working that I can do as a show as well. Could do that kind of thing as well. So that may be something we look into in the next couple of weeks here to do something like that. So yeah, we've had a lot of interesting requests the last few weeks for shows. So definitely on our list of things to do. And I have a bunch of them from a few experiences I've had the last couple of weeks. Like I said, one of them is memory. One of them is creating a web server. I actually create a web server with an Arduino now. So
all right.
So things like that.
Well, this one has been sitting around for 6 weeks waiting for me to do it. So
well, now you can get your breadboards back.
Yeah. you spend a month in the hospital, you haven't been using your bread.
Yeah. That's true.
It is a great chip to have in anybody who's doing electronics. This is a great chip to have in your arsenal of goodies. And for somebody who goes to school and starts learning about electronics, this is actually the first part of an example that is used. It was used in I don't know how many textbooks for many years, because you take a 555 timer and combine it with a decade counter, and now you've got a control for a traffic light.
Right.
And you just set the timer to be slow enough interval, and you click that decade counter very slowly. And depending on how you configure your pins, you turn on and off the two directions of a traffic light, and there you have a basic traffic light. And that's an example that's used in schools and textbooks all the time.
I would bet a lot of people don't know what a decade counter is.
Well, that may be something for another show. But essentially, it's a chip that it pulses. It sets at the first pin. You pulse it again. The output switches to the next pin. You pulse it again. It goes to the next pin. Yeah,
these days everything's microprocessor controlled, so you probably don't see that kind of stuff as much anymore as what you used to see it.
Right. You don't see it very often. But they still have their place. But you could have a fully automated traffic light with put together several 555 timers, and another example that I actually thought about this afternoon and I didn't have time to put it together, is you can have one 550 timer be the source for the next 555 timer. So the output of one can be the VCC pin of the next one. So you can daisy chain these chips on top of each other. The only thing you have to remember is that the output voltage is, roughly 1.7, 1.8 volts less than the original supply voltage. And that is something you have to, pay attention to when you're calculating, if you want an LED to be at its maximum brightness, you have to make sure you remember that voltage change on the output side.
Right. And there's potential, depending on what you're controlling, you may have to go to a transistor to turn a relay on, things like that too, because you're not going to have that same voltage level.
Yeah, and then that's right. But now that you've got that output voltage, you're right. You can use a transistor, you can turn on a relay, you can do all kinds of things, just like you could anything running off of an Arduino. So you could easily, with one of these, control a fully functional traffic light with some relays.
Right. That's how they used to do it. That's what those big boxes are in the corner.
That's exactly how they used to do it. So. Sorry.
That's okay.
And you can put a variable resistor in and change the timing on this, and have tone generators that change the frequency. That's another good example. That's another good demo that is in school a lot too.
Right. My first experience with a 555 was, like you said, with the decade counters. It was a DJ light system that was making the lights flash, and it was using the 555 with it, and it stopped working. I took it apart and figured out. I figured out what the chip was and got one and started playing with it. So I never got it fixed, but that was my first experience with it.
Yeah, they're just so flexible that you can't go wrong with them. I mean, and now we could have done the same thing with an Arduino and a little code, and probably done it easier than a 555. But the 555, you turn it on, you're done. It runs as long as it has power.
Right, and the parts don't fail for some reason.
And the parts don't fail because they're so simple. And this chip has been around since the early 70s. So That's why 1 billion plus have been sold.
Right. All right. That was great.
So there's the 555 timer.
And you could even put one of these going into an Arduino to get interrupts and things like that too, if you wanted to.
Yeah, you could.
If you don't trust the Arduino timer.
Yeah, if you don't trust the Arduino timer, or you're having trouble, with pulse width modulation, use one of these and generate whatever frequency you want, and not have to worry about the interrupts in an Arduino.
Right. All right.
Oh.
Well, that's great, Bob. Glad to have you back.
It's good to be back. You have no idea.
Yeah, you're right. I don't. All right. So I think that's all we're going to cover this week. Don't know what we're going to do for next week, but I got a bunch of things I can do. So we'll have to discuss it this week and see what we want to do for next week. But we'll figure something out. We got a long list of things we have on our list now to do. Just which one do we want to do first?
Yep. Sounds good.
All right. We'll see you, everybody.
Good night.